All right, guys, today, 3.7, we're talking about absolute extrema. So we've already talked about relative extrema, which was our maximum and minimum values in a certain range. Absolute extrema kind of plays into that same idea. So if we have f defined on our interval a to b, where c is in between a and b, then f of c is the absolute minimum if it is smaller than all the other values, all the other f of x's in that range. And f of c is the maximum in that range if it's f of c is bigger than all of the f of x's in that value. So, I mean, it's exactly what it sounds like. It's either the maximum or the minimum in the entire range, not just on a certain interval, okay? So informally, the absolute maximum is the highest point on the curve, and the absolute minimum is the lowest point on the curve. So again, it's new vocabulary, but it's obvious vocabulary. I think it's pretty easy to translate what it's talking about. So on a finite interval, just keep in mind there's always both an absolute maximum and a minimum. So whatever you're talking about, even if you're talking about people, there is always an oldest and there is always a youngest in a group of people. There's a richest, there's a poorest, there's a tallest, a shortest. There's someone that has the most siblings and someone that has the least, someone with the highest IQ and someone has the lowest. Someone will outlive everyone else. Someone will die before everyone else. Now, keep in mind, there might be two people that are the same age. And that's why up here it says that f of c for the absolute minimum is less than or equal to all the other f of x's. Because our absolute extreme can happen in more than one place. So they have that less than and greater than or equal to. That's why it includes that equal to part. So, definition of extrema. We've talked about relative extrema. Now we're talking about absolute extrema. So maximum and minimum values are extreme values. They're also called the absolute maximum and that absolute minimum. So if f is continuous, the extreme value theorem, and we'll pretend that that says theorem right there. If f is continuous on a closed interval, then f has both a minimum and a maximum. That's what the extreme value theorem tells us. Now, these spots can happen. Now, last time we looked at relative extrema. So our relative extrema can occur when f prime of x equals 0 or that f prime of x doesn't exist. And last time, that's all we checked. We only checked when it equaled 0 and when it doesn't exist. But the absolute extrema can happen at those same points, or it can also happen at the endpoints of our interval. So look at these examples right here. So I've got kind of a parabola graph right here. And down here, I have my absolute minimum down here at the bottom. That's also a relative extrema, right? That's where my f prime of x equals 0. So my absolute minimum is at one of those points, but my absolute maximum is at one of the endpoints. So we don't just have to check where f prime of x equals 0 and where f prime of x doesn't exist. We also have to check the endpoints. And this endpoint is lower, but not lower than the absolute minimum. Okay, and then over here, I actually have two places. Right here, this would be a relative extrema, and right here as well. These are places where f prime of x would equal 0. So those are relative extrema. That's a relative maximum and a relative minimum. But on my interval, my absolute maximum would be my endpoint on the right, and my absolute minimum would be the endpoint on the left. And we kind of have the same thing over here. My extrema happen, my relative extrema right here is going to also be my absolute minimum on the interval. This might keep going down after the interval, but on my interval, that's my absolute minimum. And my absolute maximum is above the endpoints at one of my f prime of x's where it was equal to 0. Okay. So first thing that we need to be careful of is that we don't just check where our derivative equals 0 and doesn't exist. We also have to check our endpoints. So when we make our table of our x's, we're also going to be just looking at our f of x. We're not interested in the signs this time. We're interested in the actual y values at those points. So we're going to be plugging things into our original function. And so we're going to plug in where our f prime of x is equal 0. We're going to be plugging in where our f prime of x does not exist. And we're going to be plugging in our endpoints and finding out what the y value is to get our minimum and our absolute maximum, okay? So now be careful. There's a note right here. It's one to keep in mind when you're reading the language of the question. You've got to make a distinction between what the absolute extrema is. So the absolute extrema is a y value. It's the absolute maximum on the graph. That's the y value. Where the absolute extrema happens is the x value. So you've got to be careful reading the question. Sometimes it will ask you where the absolute extrema is, where it happens. And other times it'll ask you what the absolute extrema value is. So you've got to make that distinction. Be careful with the language there. All right, so let's get into some problems here. It wants us to find the extrema on the interval -1 to 8. Now, if it just says extrema, it's talking about the absolute. If it had said relative extrema, then we're looking at the relative points. But because it says just extrema, I know that I'm going to also have to check my endpoints, not just the min and max in my relative situation. So it gives me my interval -1 to 8. And it gives me my f of x, 1.5x to the 2/3 minus x minus 2. So the first thing I do, just like before, is I need to use my derivative because I'm looking for where f prime of x is equal to 0 and where it does not exist, because I need to check those values. And I also need to check my endpoints, -1 and 8, which is something that we forget to do sometimes. So f prime of x. 2/3 is going to drop down and multiply by 1.5. So 2/3 of 1.5 is just 1. So that just becomes 1x to the -1/3. Minus x becomes -1, and the -2 goes away. So my derivative is just 1 over x to the 3rd minus 1, which is really just 1 over the cube root of x minus 1. So that's how I'm going to write my derivative. And maybe I shouldn't circle it. It's not an answer, but so that we know where our final derivative is at. So now I want to know where it is 0 and where it does not exist. Oops, this is a cube root. Don't forget the cube. Well, it's easy to figure out where it does not exist because in my derivative, I have this root on the bottom. This fraction cannot have a 0 on the bottom. So I've got to make sure that this value does not turn into 0. And if x was 0, it would make this 0. So x equals 0 is one of my values I'm interested in because it's going to make this not exist. It turns that bottom into 0. Now I also need to check where this derivative is equal to 0. So if 0 equals 1 over the cube root of x minus 1, I'm going to add 1 to both sides. So 1 equals 1 over the cube root of x. So now I've got to times the cube root of x to both sides. So I just get cube root of x equals 1. So what would I plug into x to get the cube root of 1? And that's just going to be 1, right? X is going to equal 1. Or if you need to take the cube of both sides, either way, I can cube the left, cube the right. Either way, I end up with x equals 1. So that's another value that I'm interested in. X equals 0, x equals 1. And don't forget to check the endpoints. X equals -1 and x equals 8. So these are the values that I need to check. And I'm going to do so. Let's kind of scroll up just a little bit so we don't use all of our space. Now I'm going to make a table right here. So my values are 0, 1, -1, and 8. I don't really care if they're in order because I'm not checking the signs. I'm just seeing which one has the biggest and smallest y value. So if I plug in a 0, I just get -2. I'm plugging these into my f of x function. I'm just plugging them into my original function, not my derivative, because I want to know the minimum and maximum of my original function. I just know that it's going to happen at one of these points. Okay. So -2, if I plug in a 1, you know what? Let's just plug this in here. 1.5x. We're going to have to plug in quite a few numbers here, so we might as well just save us a little bit of time other than you having to watch me type in a function. So if I go to the table, I don't want to go to the graph because I don't want you to see what it looks like yet. But if I plug in 0 and I plug in 1 and I plug in -1 and I'm going to plug in 8. So I get -2, I get -1.5. At -1, I get a 0.5. And at 8, I get -4. So -4 is my minimum. That's my smallest number. And 0.5 is my maximum. So my minimum and my maximum are actually happening at my endpoints. They're not happening in between. They're actually happening at those endpoints. So I'm going to, now remember the AP test doesn't pull information from a table. You can't just give them this table. You have to say f of 8 is equal to -4, and that's my absolute minimum. And f of -1 is equal to 0.5, and that's my absolute maximum. Okay. So if it's asking for the extrema, it's not asking where it happens. It wants that value. So be careful that you don't give them a point. You make sure that you give them the value, the absolute extreme, which is -4 and 0.5. It's weird that the 0.5 is my maximum, right? It almost feels like that would be smaller, but we've got our negative sign. Okay, moving on to a cosine function, because why not? We haven't done trig in a few videos here. So it wants us to find the extrema. Again, it doesn't say relative extrema, so I'm going to consider my endpoints, and I'm looking for the largest and the smallest values on that interval. Oh, let's double check this first one before we move on. If I look at the graph, I've got my highest point here on the left. Let's change our window so it matches. I'm only supposed to go from -1 to 8. So if I look at that graph, on the left, that's my maximum. And then if you notice right here at 0, where we had our graph wasn't going to exist, right there at 0, we have a cusp. And that's why we had a does not exist. Our derivative didn't exist at that point. And then at 1, right here, my slope is going up. I'm increasing. And then at 1, I flatten out, and then I start going down. So there's a little bit of a concavity right there where it goes up and then it goes back down, which looking at the graph, you almost don't see it, but we know it happens because we know that horizontal tangent line right there. And then obviously our low point is there at the end. So, all right, moving on to the algebraic side of this. So cosine squared of x, remember, first thing I want to find is my derivative. And cosine squared of x, sometimes, and maybe we should rewrite this first, because cosine squared of x is great to remind us that we're squaring the whole thing, not the x. But remember, that means cosine of x squared plus sine of x. So when I take the derivative, f prime of x, I bring the 2 in the front, and I get cosine of x. So I do the outside derivative, and then my chain rule tells me I have to multiply by the derivative of the inside, which is negative sine of x, because the derivative of cosine is negative sine. And then I'm going to add the derivative of sine of x is cosine of x. Now, just to kind of help myself out, because I know I'm going to set this equal to 0 soon, I want to look for, I can factor out a cosine and a cosine. So f prime of x is going to equal, if I factor out that cosine of x, I'm left with -2 sine of x plus 1. And I think that's about as simplified as I'm going to get. So I need to check where my derivative equals 0. I need to check where it does not exist. And I need to check my endpoints. So I've got my endpoints figured out. I already know what those are. They tell me what those are. So I've got to figure out when this is not going to exist and when it's going to equal 0. All right. So let's go ahead and if I set this equal to 0, -2 sine of x plus 1. So that means cosine of x could be 0. And that also means that -2 sine of x plus 1 could be 0. So if I minus 1 and then divide by -2 to get sine of x by itself, I end up with sine of x equals 1 over 2, because the negative is going to be divided by a negative, so it changes it to a positive. So what x value makes sine of x equal to 1/2? So if I look at my unit circle, I'm going to get a sine, which is my y value. Remember, that's your y value. My y value is going to be 1/2 at, what are we, at pi over 6. And it's going to happen again because I'm going all the way to 2 pi at 5 pi over 6. So those are going to be my two x values I check for this one. This one, to make cosine of x equal to 0, that's going to happen at pi halves. X is going to equal pi halves, and it's going to happen again at 3 pi halves, right? Because it happens when we're straight up at 90 and when we're straight down at 270. So pi halves and 3 pi halves. So those are the four that I'm going to check, as well as my endpoints. As far as not existing, I don't see anything that I need to worry about because I don't have any fractions on the bottom that are going to end up being 0. So I'm not worried about areas that don't exist. I'm just worried about these four, and then, of course, my endpoint. So my table, x and f of x, and I can probably give myself a little bit more room. Let's scroll down. There we go. X and f of x. So x, I'm going to, and I don't really care if these are in order. I can put them in order, 0, pi over 6, and then we're going to have pi halves, and then I'm going to have 5 pi over 6, and then I'm going to have 3 pi halves, and then I'm going to have 2 pi at the end, right? Is that 6 values? 1, 2, 3, 4, 5, 6. All right. So I can plug all of these in by hand, but I don't want to. So I'm going to rewrite. Remember, I'm plugging these into my original function because I want to know my extrema. I want to know my highest value and my lowest value. So if I put in here cosine of x squared, and then I've got to add sine of x. And then I'm going to not accidentally hit graph because I don't want you to see it quite yet. So if I go to the table, I want to check 0. I want to check pi over 6, and I can just put that right in, pi divided by 6. It'll round it for me. Pi divided by 2. 5 pi divided by 6. 3 pi halves. And 2 pi. So I put all of those in, and it should give me my 6 values. So at 0, I'm at 1. At pi 6, I'm at 1.25. At pi halves, I'm at 1 again. At 5 pi 6, I'm at 1.25. And this is pretty normal of a sine and cosine graph, right? Because they're usually some sort of wave, I'm not surprised to be getting the same values more than once. At 3 pi halves, I drop down to -1, and at 2 pi, I'm back up at 1 again. So when I look at these values, -1 is my minimum, but I have my maximum happens at 2 different values. And I don't really care where it happens because it just wants me to find my extrema. So I can say that f of pi over 6, comma, 5 pi over 6 is equal to 1.25, which is my absolute maximum. Okay, 1.25 is my absolute maximum. And I just want to show, they're not going to pull it from the graph, from the table. I just want to write where I got that from. Okay, and then f of 3 pi halves is equal to -1, which is my absolute minimum. So -1 is my absolute minimum, and 1.25 is my maximum. So if I look at what this graph looks like, let's change our window to go from 0 up to 2 pi. And I'm going to change my x minimum and maximum just a little bit. I'm going to make my x minimum, let's just go -2. And let's make my y maximum 2, just so we can kind of see what it looks like a little bit better. So we've got that curve. I've got this up and down at the top, and that's why you get your maximums in 2 different places, and then it drops down. And then this pattern, if I were to zoom out, it's going to just keep repeating itself. If I were to go, instead of 2 pi, if I were to go to, let's say, 8 pi, so we're going to go 4 periods out, you're going to see that pattern repeat, 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 repeat. It kind of looks like an x-ray of someone's mouth. Anyway, so those are your absolute maximum and your absolute minimum. So this time it didn't happen at the endpoints. It happened in the middle, even though, well, that's kind of what we would have expected on that one. Okay, so moving on, let's do some more. A particle moves along the x-axis with the position function on the interval 0 to 3. And it gives us our function. So this is my position function, okay? This is telling me where my particle is. And it wants to know, when is it furthest to the right and furthest to the left? So I'm looking for my maximum and my minimum position. So I've got to take the derivative of my position. So x prime of t is going to be 4t cubed minus 12t squared plus 12t, and the minus 10 is going to just disappear. So there's my derivative. Now to find the max and min, I've got to check, I need to know where f prime of x is equal to 0, where it maybe doesn't exist, and of course my endpoints to figure out my maximum and my minimum. So I know my endpoints. I know I'm going to check 0 and 3. That's given. So I'm going to check 0 and I'm going to check 3. I don't see any places where my derivative is not going to exist, because I just have a polynomial. So my derivative is going to exist everywhere. There's no divisions to worry about the bottom becoming 0. So let's set this equal to 0. 0 equals 4t cubed minus 12t squared plus 12t. So just like before, we're going to try and factor out. So I'm going to pull out a 4t so I can get something being multiplied together. So I'm left with t squared minus 3t, and then I'm going to add 3. And those are going to equal to 0. Now this one here in the middle, that's not going to factor nicely. T squared minus 3t plus 3. I'm not going to be able to break that down quickly with my x factor. I could use the quadratic formula, and you are allowed in the apps, you're allowed to use the polysmelt. This one down here on number 9. I don't know what number it is on your calculator, but you should have it. The polysmelt, it gives you a root finder. So I can go to root finder and hit enter, and it asks what my order is. So my largest root, I'm just looking at these parentheses. I want my roots. My largest order is 2. So I'm just going to go down to next. So I hit the graph button. And then yours might look a little bit different than mine. Mine, it actually shows the polynomial up here. Yours might just ask for the values. So x squared in front of my x squared is just a 1. So I hit enter. And then there's a minus sign. So I hit enter. And then a 3, enter. And then I've got a plus, enter, and my constant is 3. So then when I hit solve, it tells me that there are no real roots. So that means that these right here are just going to give me imaginary roots, which if you were to do this by looking at the graph, if I were to go all the way back to my y equals, and if I were to graph 4x cubed, and maybe we're taking more time than we need to, but just so you can see, there's multiple ways to figure this one out. If I wanted to know where, actually, I don't want that whole thing. I just want to know where this part equals 0. So if I put in x squared minus 3x plus 3, if I want to know where that is equal to 0, I can graph it. But when I look at my graph, let's zoom standard. It doesn't ever equal 0. It never crosses the x-axis. This part right here is never going to cross my x-axis. So I don't actually get any values from that part at all. The only one that I've got to check is when 4t is equal to 0, which means I need to check when t is equal to 0. And maybe I should make this this is t and f of t, right? Or x of t, I guess. Use the right labels here. I'm already checking 0 because that's one of my endpoints, right? And really, that's all there is to check. So if I go ahead and go back to my y equals, and if I'm going to plug in my original function, 4x cubed minus 12x squared, no, minus, please, minus 12x squared plus 12x. No, that's my derivative. Oh my gosh, my original function. Clear up here. This is what we're plugging in. X to the 4th minus 4x cubed. That's the last thing we need, is to get mixed up in what function we're using again. Minus 6 or plus 6x squared minus 10. So my original function, if I go to the table, I want to check what happens at 0 and what happens at 3. So at 0, I get negative 10, and at 3, I get 17. And those are going to be my minimums and my maximum. So this one asks, when is this the furthest to the right and furthest to the left? So at t equals 0, I am furthest left. At t equals 3, I am furthest to the right. That would be the answer that I submitted. At t equals 0, I'm furthest left. At t equals 3, I'm furthest right. And again, they don't pull the information from here, from the table. So we might want to say that x of 0 equals negative 10 and x of 3 equals 17. So that's when it happens. Now it says, what is the maximum? And that just comes back to reading the question carefully. That when word right there tells me that they don't care what the minimum and maximum are. They just want to know when it happens, which is my t value. So part B says, what is the maximum and minimum velocity? And I like this question because we're trying to maximize and minimize the velocity. So my velocity function is my derivative right here from my position, right? Position, when I take the derivative, I get the velocity. So my velocity function is just 4t cubed minus 12t squared plus 12t. So to check the maximum and minimum velocity, I'm going to take the derivative of the velocity. So that's 12t squared minus 24t plus 12. That's my derivative. So I'm interested, where is v prime equal to 0? Where does it not exist? And again, I'm interested in my endpoints to check my maximum and minimum velocity. So set this equal to 0. 0 equals 12t squared minus 24t plus 12. I can factor out of 12, which is nice because then I just get 12 squared minus 2, or t squared, 12 squared. T squared minus 2t plus 1 equals 0. 12 is just going to divide away. And so t squared minus 2t plus 1, well, that factors. That just becomes t minus 1 and t minus 1, right? So I get the same factor twice. So when t minus 1 is equal to 0 is when t equals positive 1. And that happens at 2 points, but I don't need to check both of them because it's the same point. So that's one of the values I'm going to plug in. So in my velocity function, my time, now I'm plugging stuff into my velocity function. I'm going to plug in my endpoint, 0 and 3, and I'm also going to plug in this value 1, this relative extreme value right here, right? This was one of, what did we call those? Critical values. That's one of my critical values that I need to check. So my new function, I'm going to go back to y equals, and I'm going to plug in my velocity function because that's what I'm checking the maximum and minimum of. So 4x cubed. And I know this video, you're just watching me type in a lot of stuff. I'm okay with that. You can fast forward if you want to. Plus 12x. So when I go to the table, I want to check 0 and 3, which it already is doing for me, and I want to check 1. So at 0, I'm getting 0. At 3, my velocity is 36. And at 1, my velocity is 4. So my minimum velocity is happening right there. My maximum velocity is happening there at the endpoint, which is kind of what we might expect with a polynomial function because of that exponential growth. A lot of times that endpoint is going to be our maximum. So what is it asking for? This one is asking what the maximum and minimum velocity is. It's not asking where it happens. It wants to know what the actual value is. So I would say that at v of 3, I get 36, which is my maximum velocity. Whoops. V of 3, I get 36, which is my maximum velocity. Again, it's not interested in where. It's interested in what the maximum is. And it also wants to know the minimum. At v of 0, I get 0, which is my minimum velocity. All right. Moving on. What is the maximum and minimum acceleration? Again, I like where this question goes because, in fact, you have to do something that we've never done before. We know that the derivative of my velocity. So this equation right here is the derivative of my velocity. So we have our position function, x of t. When I take the derivative, I get my velocity. When I take the derivative of velocity, I get acceleration. So my acceleration function, and I'm going to write it down here so I don't forget. My acceleration function is my derivative of my velocity function. So 12t squared minus 24t plus 12. But to check the maximum and minimum of my acceleration, I have to take the derivative of acceleration, which we've never done before. So I'm going to take a prime of t, and that's going to be 24t minus 24. Now, the derivative of acceleration, it actually has a name. We call that torque. Just like we have position, velocity, acceleration, the derivative of acceleration, what comes next is torque, which is something that you've probably heard when people are talking about big muscle cars and things like that. We talk about the torque. You talk about torque when you are dealing with a lot of times with things that have to rotate or create when you're trying to, like when you're taking off a tire and you extend that tire iron to be longer because it gives you more torque, right? So our torque is our derivative, a prime. So again, I'm looking just like all these other ones to find the maximum and minimum, blah, blah, blah. I'm looking for when my a prime equals 0, when it doesn't exist, and of course my endpoints. And I'm going to plug all of those values into my acceleration function because that's what I'm trying to maximize. So 24t minus 24 equals 0. So if I just add 24 to both sides and then divide by 24, t is going to equal 1. Okay, so I'm interested in when t equals 1 and my endpoint 0 and my endpoint 3. I don't worry about not existing because, again, it's just a polynomial function. It always exists. So I'm going to plug those in at time. Those are my times, and I'm plugging them into my acceleration function. So 0, 1, and 3. I go to my y equals, and you can plug these in. You're welcome to just plug them in, but I want you to see it both ways. So if I plug in a 0, algebraically, 24 times 0 is 0, minus 24 is negative 24. If I plug in a 1, 24 times 1 is 24, minus 24 is 0. If I, oh, whoops, wrong function. Oh my heck, guys, we got to watch ourselves. Like, wait a minute, this seems too easy. I'm plugging these into A. Got to slow down a little bit. We're plugging these into A. That would have been my torque at that point, but I want to plug these into A, and I don't want to plug all of those in by hand. So yeah, I'm going to use my calculator. 12 x squared. You're welcome to do them by hand, or you can fast forward the video. So if I go to my table, and I'm going to plug in 0, I'm going to plug in 1, and I'm going to plug in 3. And I'm going to get at 0, I have an acceleration of 12. At 1, my acceleration is actually 0. And at 3, I have an acceleration of 48. So that's kind of interesting. All these other ones, our max and minimums happened at the endpoints. But this one, my acceleration, the minimum, is actually in the middle. It's at the value of 1. So I would say that A of 1 equals 0, which is my, let's see, how did they word it? Let's see, they didn't call it absolute, they called it minimum acceleration. So I would say A of 1 is equal to 0, which is my minimum acceleration. And A of 3 is equal to 48, which is my maximum acceleration. So I would say 48 is my max acceleration and 0 is my minimum acceleration, because it wants to know what those accelerations are, not where it happens.